Hello everyone, welcome back. This is my 47th lecture on the partial differential equation. Today we are going to discuss the topic method of separation of variables for wave equation. In the previous lectures we discussed the method of separation of variables for heat equation. Also we solved the heat equation by using the method of separation of variables. Now here we are going to discuss the method of separation of variables for wave equation. Okay, so consider the wave equation utt minus c square into uxx equals 0 for x varies from 0 to L, that is a finite string. Okay, that is wave equation for a finite string and t greater than 0. Okay, this is the time variable. With the boundary conditions ux 0t equal to lt equal to 0. That means when x equals 0, then ux equals 0, and when x equal to L, then ux equal to 0. Okay, for t greater than or equal to 0, and the initial conditions are given by ux0 equal to f of x. That is when t equals 0, the amplitude of the function u is f of x, and when t equal to 0, then ut equal to g of x. Okay, that is the velocity is g of x initially. Okay, so that is f and g are the given functions which are the initial data, and c is a post-t constant. So we already discussed in the previous lecture that this type of boundary conditions are called Newman boundary conditions. Newman boundary conditions. Okay. Okay. Now this 1 to the equations 1 to 4. That means this wave equation along with the boundary initial boundary value conditions. Okay. This is these two are initial conditions and these are the boundary conditions. Now this is a linear homogeneous initial value or initial boundary value problem. Okay. Now here the compatibility condition are given by f dash of 0 equals 0, f dash of L equals 0, g dash of 0 equals 0, and g dash of L equals 0. This is because we are given the initial condition is f of x and the and the g of x, and the boundary conditions are ux 0 t equal to ux L t equal to 0. So this initial condition is compatible with this boundary condition only when f dash of 0 equal to 0. That is f dash of x is equal to ux x is 0. That means which is from this we get 0. And g dash of x is also ut x is 0. So g dash of 0 is equal to 0. And therefore similarly we have f dash of L equal to 0 and g dash of L equal to 0. Okay, so we have this compatibility condition. Now to solve this PDE or the wave equation, we can consider u equal to xt x of x into t of t as the solution. Okay, by separation of variables, where x is a function of small x only and t is a function of small t only. Okay, so let u equal to x into t be a non-trivial solution of the PDE 1. Okay, so equation number 1 can be written as this is equation number 1, our PD utt minus c square into uxx equal to 0. So that can be written as we have uh, x into t double dash, that is this is utt minus c square into uxx equal to 0. So x into t double dash minus c square into x double dash t equal to 0. So separating the variables we can write this as x double dash by x is equal to t double dash divided by c square into t. Okay, so we can find a constant lambda such that this is equal to minus lambda. Okay, so we have a system of two equations or differential equations. First is x double dash by x is equal to minus lambda, that is x double dash plus lambda x equals 0, and the second one is t double dash by c square into t equal to minus lambda. So from this we get t double dash plus c square into lambda into t equal to 0. Okay, so for 0 less than x less than L and t greater than 0. So the first equation is it's a differential equation with the capital X and small x. Small x as the independent variable and capital X as the dependent variable, and the second is the differential equations in dependent variable t and small independent variable small t. Okay, so now we have given the boundary conditions ux0 t equals 0 and ux lt equals 0. That at the boundary points 0 and L we have ux equals 0. Okay, that means we have our solution is u equal to x into t. Therefore, ux is nothing but x dash into t. That is x dash ux is equal to x dash into t. Therefore, applying this condition, we have x dash 0 into t of t equal to 0. And applying the second condition, we have x dash at L into t of t equal to 0. Clear? So from this, we have x dash of 0 equal to 0, and from this we get x dash of L equal to 0. Otherwise, we will get a trivial solution, because if this is x dash of 0 is not equal to 0, then we have t of t equals 0. Then t of t equals 0 implies from this we get u equals 0. So the solution will be trivial. So we are seeking a non-trivial solution. So here we will get x dash of 0 equal to 0 and x dash of L equal to 0. Here also, if this is not equal to 0, we will get t equal to 0. That means u equal to 0. So we will get only trivial solution. Okay, so we have x dash of 0 equal to 0 and x dash of L equal to 0. Therefore, the function x should be a solution of the eigenvalue problem x double dash plus lambda x equals 0 along the boundary conditions x dash of 0 equal to 0 and x dash of L equal to 0. Clear? Okay. So this eigenvalue problem is also called Newman problem. Okay. Now we are considering three different cases for lambda, as in the case of heat equation. Okay. So first we are considering lambda equal to 0. Okay, that is we are considering 0 eigenvalue. Okay, 0 eigenvalue. So when lambda equal to 0, we have x double dash is equal to 0, and therefore x is equal to c1x plus c2, where c1 and c2 are arbitrary constants. So therefore x dash is nothing but c1. So x dash of 0 equal to 0 implies c1 equal to 0, and x dash of L equal to 0 implies c1 equal to 0. That means c2 is arbitrary. Therefore x is equal to c2, where c2 is arbitrary. Okay, so the solution of this eigenvalue problem when lambda equal to 0 is x equal to an arbitrary constant. So lambda equal to 0 is an eigenvalue with unique eigenfunction x equal to 1. Okay, that is the eigenfunction is unique up to a multiplicative factor, because we can write this x the solution or the eigenfunction as any number. Okay, so that is we can express this x is equal to c2 into 1. So the independent eigenfunction can be written as x equal to 1. Okay, so we obtain that here when lambda equal to 0, the solution is not trivial. Therefore lambda equal to 0 is an eigenvalue with the eigenfunction x is equal to 1. Clear? Now consider the second case when lambda is less than 0. So we are considering negative eigenvalues. Negative eigenvalues. Okay, that means this differential equation is x double dash plus lambda x equal to 0. So solving this, we will get x is equal to c1 e to the power square root of minus lambda x plus c2 e to the power square root of minus lambda x, because the auxiliary equation corresponding to this differential equation will be m square plus lambda equal to 0. That means m square equal to minus lambda, but we have lambda is less than 0, so this minus lambda is greater than 0. Therefore m has the values plus or minus square root of minus lambda. Okay, so we have the solution as c1 into e to the power this square root of minus lambda into x plus c2 into e to the power minus square root of minus lambda into x. So we have since to apply the boundary conditions, we can take the first derivative x dash is nothing but c1 into square root of minus lambda into x into e to the power square root of minus lambda into x plus c2 into e to this into derivative of this, which is minus square root of minus lambda. So this is x dash now. So applying these conditions, x of 0 equals 0 implies when x equals 0, we have this is e power 0 is 1, so we have c1 square root of minus lambda minus c2 square root of minus lambda equals 0. So since lambda is not equal to 0 here, we can write this as c1 minus c2 is equal to 0. Okay. Now this applying the second condition, x of L equal to 0. That is c1 square root of minus lambda into e to the power square root of minus lambda into L minus c2 square root of minus lambda into e to the power minus square root of minus lambda into L equal to 0. Here also we can divide square root of minus lambda, and we can write this as c1 e to the power minus square root of minus lambda L minus c2 e to the power minus square root of minus lambda L. So we have obtained a system of equations in c1 and c2. Okay. So to find the values of c1 and c2, we can find the corresponding determinant. It will be 1 minus 1, and here c1 sorry, e to the power square root of minus lambda into L, and the last compound is minus e to the power minus square root of minus lambda into L. So we have the determinant of this is nothing but e to the power minus e to the power minus square root of minus lambda into L minus minus, that is plus e to the power square root of minus lambda into L, which is not equal to 0. Okay, so we have the solution of these two systems. This system of two equations will be unique since the determinant is not equal to 0. So we have c1 equal to c2 equal to 0. Okay, solution is unique, which is c1 equal to 0 and c2 equal to 0. So that means we have from this x is equal to 0. Okay, so solution is trivial when we take lambda as, we consider lambda as negative. So if lambda is a negative number, then it will not be an eigenvalue, because we obtained the function as the trivial solution. This solution is trivial. So lambda less than 0 is not a any negative number is not an eigenvalue. Okay. Now consider the third case, lambda greater than 0. That is, we are considering positive eigenvalues. Positive eigenvalues. Okay. So in that case, we'll get the auxiliary equation is m square plus lambda equal to 0. That implies m square is equal to minus lambda. Since lambda is greater than 0, we have minus lambda is, yeah, here is a mistake, I think. Yeah, m square is minus lambda, which is less than 0. Therefore, m is equal to plus or minus I into square root of lambda. Here, so we'll have the solution as, this is complex conjugates. So the solution will be c1 into cos square root of lambda into x plus c2 into sin square root of lambda into x. So to apply the initial boundary conditions, we can find the derivative at first. So x dash is equal to minus c1 into square root of lambda into sin square root of lambda x plus c2 into root of lambda cos root of lambda x. Okay, so applying the boundary conditions, first condition is x dash of 0 equal to 0. So when x equals 0, we have sin 0 is 0, and when x equals 0, cos 0 is equal to 1. So we have c2 into square root of lambda equal to 0. Since square root of lambda is not equal to 0, because lambda is greater than 0, we have c2 equal to 0. Okay, so we have x is equal to c1 cos square root of lambda into x only. So applying the second condition, we have x dash of L equals 0. That means we already obtained that c2 equals 0. So minus c1 into square root of lambda into sin square root of lambda into L equal to 0. Okay, so from this we have sin square root of lambda into L equal to 0, because if c1 is a 0, then we have x equal to 0, because c2 is already 0. So x will be trivial, solution will be trivial. So c1 may not be equal to, it need not be 0, should not be 0. And if lambda is also non-zero, because we are taking lambda is greater than 0. So this sine of square root of lambda into L equal to 0. This implies square root of lambda into L is equal to n into pi, where n belongs to n. Okay, we are not considering here as n equal to 0. If we are considering n equal to 0, we have lambda equal to 0, but this is not the case. Lambda is greater than 0 here. So and also if we considering n as negative, then also we'll get the same values for lambda. Okay, so we are taking only n belongs to n. So lambda equal to, so from this we get square root of lambda is equal to n pi by L, and therefore lambda equal to n pi by L whole square. Okay, for n equal to 1, 2, 3, etc. So the solution is not trivial only if lambda equal to n pi by L whole square. That means these values of lambda are eigenvalues. Okay, these are isolated eigenvalues. For n equal to 1 we have pi square by L square, n equal to 2 we have 4 pi square by L square, etc. Okay, so for n equal to 1, 2, 3, etc. we have a sequence of eigenvalues lambda equal to n pi by L whole square. Okay, so the corresponding eigenfunctions will be obtained by replacing the value of lambda in equation number 10. Okay, that is we already obtained that C2 equal to 0. So x is equal to C1 into cos root lambda into x, where root lambda is n pi by L. So cos n pi by L into x. So we have x is equal to C1 cos n pi x by L for n equal to 1 to 3, etc. So this will be the corresponding eigenfunction. So we have obtained that the eigenvalues are lambda n is equal to n pi by L whole square for n equal to 0, 1, 2, 3, etc. We are also included the value 0 for n, because when n equals 0 we already obtained that lambda, when n equals 0 we have lambda naught is equal to 1 and corresponding eigenvalue eigenfunction will be 1. Sorry, uh, lambda naught equal to 0 and corresponding eigenfunction will be 1. We already obtained that. So when n equals 0 we have lambda naught equal to 0 and corresponding eigenfunction will be x0 of 0 equal to x0 of x is equal to cos 0, which is 1. Okay, so we have included the eigenvalue lambda equal to 0 also here. So the eigenvalues of the problem are lambda n equal to n pi by L whole square for n equal to 0, 1, 2, 3, etc. And with the corresponding eigenfunctions, xn of x is equal to cos n pi by x, n pi x by L, so for n equal to 0, 1, 2, 3, etc. And this eigenfunction is uniquely determined up to a multiplicative factor, this C1. Okay, up to a multiplicative factor. Okay, now consider the differential equation 8, that is the second this is second differential equation in that system, that is with respect to t, that is t double dash plus c square lambda t equals 0. So here we are going to replace or apply the eigenvalues lambda, these eigenvalues, okay, lambda naught and lambda n for n equal to 1 to 3, etc. to here. So when first we apply lambda equal to 0, that is lambda not equal to 0, then we have t double dash is equal to 0, therefore t equal to c1 plus c2 t. Okay, for c1 and c2 are arbitrary constants, so for convenience we are taking this as t naught. Okay, denoting this as t naught. Now for lambda equal to lambda n, we have lambda n is actually n pi by L whole square, right? So n pi by L whole square. When lambda is greater than 0, we have n pi by L whole square. So applying this we get t double dash, we already obtained that. From this we get when lambda is greater than 0, we have the solution of this will be c3 into cos c square root of lambda t plus c4 sin square root of c square root of lambda t, because here the auxiliary equation is m square plus c square lambda equal to 0. From this we have m square equal to minus c square into lambda less than 0, because lambda is greater than 0. So we have m is equal to plus or minus I into c square root of lambda. So we have the solution as t equal to c3 cos c square root of lambda into t plus c4 sin c square root of lambda into t for n equal to 1 to 3, etc. Okay, this is for the so when we apply root lambda is equal to lambda n is equal to n pi by L. So root lambda equal to uh, lambda n is equal to n pi by L whole square. So root lambda is equal to n pi by L. So we have here c3 into cos n pi ct by L plus c4 sin n pi ct by L, replacing the value of root lambda. Okay, root lambda is n pi by L, right? So the solution of the initial boundary value problem, our the first problem is 1 to 4, right? The initial boundary value solution of this initial boundary value problem is we have u equal to x into t. So we are splitting the solution as when lambda equals 0 and when lambda greater than 0. Okay, you already obtained that when lambda is less than 0, no solution. Okay, that is solution is trivial, so no eigenvalue, eigenfunction. So the solution u equal to, or u of xt is equal to, when lambda equals 0 we have x naught into t naught, and when lambda equal to lambda is greater than n, that is when lambda equal to lambda n, we have x n tn. So replacing that values, we will get a naught plus b naught t divided by 2. Actually we have, when lambda equal to 0, we already obtained that t naught is equal to c1 plus c2 t, and x naught is equal to 1, right? So 1, or we can use any constant c. Okay, so the solution, if you take this constant c as 1 by 2, we will have a naught by 2, a naught plus b naught t divided by 2. Okay, uh, so for lambda equal to lambda naught, which is equal to 0, we have this as the solution. And when lambda greater than 0, or when lambda equal to lambda n, which is greater than 0, we have the solution will be xn into tn. We already obtained that xn is this. Yeah, this is xn cos n pi x by L, and tn is C3 cos n pi ct by L plus C4 sin n pi ct by L. So we have to multiply this Tn with those that Xn. So we'll get this cos n pi x by L into this. Okay. So we'll get this as solution as cos n pi x by L into an cos n pi ct by L plus bn sin n pi ct by L. Okay, where an and bn are constants. Now, so applying the generalized superposition principle, we have this. This is a, so actually this is a solution when lambda equal to 0, and when lambda equal to when lambda is greater than 0, we have these as solutions. So for different values of n, for lambda equal to when n equal to 1, we have for the value for lambda 1. So by the generalized superposition principle, the sum of these solution will also be a solution. So the general solution or generalized solution will be obtained by adding all these solutions. So our generalized solution will be u of xt is equal to a naught plus b naught t divided by 2 plus summation summation n from 1 to infinity, this a n cos n pi ct by L plus b n sin n pi ct by L into cos n pi x by L. So we have infinitely many terms in this solution. Okay. So we have obtained the solution u of x equal to a naught plus b naught t divided by 2 plus summation n from 1 to infinity a n cos n pi ct by L plus b n sin n pi ct by L into cos n pi x by L. Okay. So next step is to find the coefficients a n and b n for n is equal to 0, 1, 2, 3, etc. Okay. Uh, for that we need to use our initial conditions, so that we can discuss in the next lecture. Okay, thank you.